A clip starts with keyboard typing. Then a person asks, "What is this sound?" The expected response is, "It is a keyboard." A transcript would contain only the spoken words. "What is this sound?" The requested answer also needs the keyboard sound. The model must identify that sound and treat the words as an instruction. Qwen2-Audio accepts audio with text if the user provides it and produces text. This video answers 3 questions. How is the audio passed into the language model? How does training teach the same model to analyze audio or answer a spoken request? What do the tests show it can do? And where does it still fail? The processor resamples the clip to 16,000 samples each second. It then measures sound energy across 128 frequency bands and lays those measurements out over time. These MEL features sit inside a fixed 30-second input window. Audio after 30 seconds is cut off by default. An audio encoder based on Whisper Large V3 reads the MEL features and compresses them. 1 second of audio becomes about 25 audio vectors. A 20-second clip therefore becomes 500 audio vectors. Each audio vector is 1,280 numbers wide. A single learned linear layer maps it to 4,096 numbers, the same width as the language model's text embeddings. The projector keeps all 500 positions and changes only the width of each vector. The serialized input contains one special audio placeholder for this clip. Before decoding starts, that placeholder expands into the clip's 500 projected audio vectors. These continuous vectors are called soft tokens because they are not vocabulary IDs. The decoder receives the soft tokens in the same sequence as the text embeddings, then generates the response as text. Attach the keyboard clip and add the text instruction, "Identify the sound." The text tells Qwen2-Audio what to do with the audio, so the clip is the material being analyzed. This input pattern is called audio analysis. Now remove the text instruction. The audio itself contains the spoken question. What is this sound? Qwen2-Audio treats those spoken words as the user's request and answers in text. This input pattern is called voice chat. One processor and one Qwen2-Audio model handle both user turns. Neither behavior needs a system prompt that selects a mode. The model has learned from the user turn whether to treat the audio as content to analyze or the spoken words as the request to answer. Start with a car horn and the instruction, "Generate a caption in English." In the first training stage, Qwen2-Audio sees audio, an ordinary language instruction, and the target text it should produce. The reported pre-training audio includes 370,000 hours of speech, 10,000 hours of sound, and 140,000 hours of music, 520,000 hours in total. Supervised fine-tuning then trains the model on both user turn patterns together. Some examples pair audio with a separate text instruction for audio analysis. Others put the spoken request inside the audio for voice chat. Finally, direct preference optimization uses one input and 2 candidate responses. Human annotations mark one response as preferred and the other as rejected, and training favors the preferred one. The paper does not isolate any stage with a controlled ablation, so it does not show what each stage contributes by itself. On Airbench, the paper's Qwen2-Audio system averages 6.93 out of 10 across speech, sound, music, and mixed audio. Qwen2-Audio Chat averages 6.34. Airbench uses GPT-4 to score the open answers, and the public checkpoint has a separate result block. The independent MMAU main test has 9,004 choice questions about speech, sound, and music. Qwen2-Audio Instruct scores 52.50%, while the base checkpoint scores 6.20%. The base model often does not choose one of the listed answers, so this test shows how strongly usable forced choice behavior depends on instruction alignment. MMAU keeps the written question and choices the same, then replaces the real audio with Gaussian noise. Qwen2-Audio Instruct accuracy drops. The drop shows that audio contributes to its answers on this test. On MMAU's separate 1,000 question mini-split, Qwen2-Audio Instruct scores 49.20%. 8 university students average 82.23% on the same questions. The MMAU authors manually review 500 Qwen2-Audio Instruct cases. In that audit, 55% of the errors are labeled perceptual and 18% are labeled reasoning errors. Keyboard typing comes first. Then the spoken question, "What is this sound?" The audio encoder compresses both parts. The projector maps the resulting vectors into soft tokens. The language model reads those vectors, treats the question as the request, and generates the text. It is a keyboard. Qwen2-Audio's main advance is learned routing inside one audio to text model. A separate text instruction makes the clip material to analyze. In an audio-only user turn, speech inside the clip can be the request the model answers. The output remains text, and released pre-processing truncates longer clips to 30 seconds by default. The tests support broad capability without establishing human-level audio understanding, and perception errors remain unresolved. Qwen2-Audio is a broadly trained and aligned audio-to-text model that learned when to analyze and when to answer.